So moving along here, so let's go over those learning goals that I talked about in this first video, okay? So let me get my highlighter here. Okay, be able to interconvert between pressure units using the process of dimensional analysis. So I didn't do a whole lot of, oh, I need my highlighter, there we go. I didn't do a whole lot of examples in my lecture. I'm going to give you some examples of these in the discussion, okay? But it's the same process we've been using for interconverting units, okay? So know the individual gas law. So I want you to know the name and the equation. So Boyle's law. Pressure is inversely proportional to volume. Charles' law. Volume is directly proportional to temperature. Avogadro's law. Pressure is directly proportional to temperature. And Avogadro's law. Volume is directly proportional to moles. So know those and be able to use them in calculations. Okay? And I just kind of started getting into the ideal gas equation and the combined laws. I'm going to get into that in more detail now in this lecture. All right? Okay, so we have this ideal gas law. Okay. PV equals nRT. Famously, people call it PIV-NERT. PV equals nRT. And what I want to point out, when using this equation, most of the time, so I'll say most of the time, we're solving for moles, right? Because this is a chemistry class, right? And so when we start using this equation in problems, that's really what we want. We want to get the number of moles so that we can do a reaction stoichiometry calculation, right? But now that being said, we could still be solving for temperature, volume, or pressure. So the gas constant is a constant, so we're not really, we use it, but we don't ever really solve for it. But recognize with this equation, if you want number of moles, right, you have to have pressure, volume, and temperature. If you want temperature, you have to have moles, volume, and pressure, and so forth, right? So you kind of have to think of all of the things that you have to be able to use this equation. And what I want to point out, okay, as far as the units for this gas constant, I'm going to do a little bit of algebra here, and I'm going to divide both sides by by NT, okay? And so when I do that, that's R, PV divided by NT equals R. So then what about the units? Well, pressure, we're going to use atmospheres. Volume, we're going to use liters. N for moles, we're going to use moles. And temperature, we're going to use Kelvin. Okay? So look at the unit right here. This is why I circled this value, the 0.08206 liters times atmospheres divided by mole Kelvin. Okay, so that's where that unit comes from. And so we notice that there are other flavors, that as I like to call, the other flavors of R, and it's just involved in using different units in the PV equals nRT equation. Okay, so these are the units that we prefer to use. Okay, atmospheres, liters, moles, and Kelvin. And then that way, when we use this equation, we're going to use the value 0.08206 for R. Okay? So let's move forward. So from this equation, we generate what's called STP, standard temperature and pressure. And as it turns out, standard temperature is not room temperature. It's 273.15 Kelvin. That's 0, I can't write. That's 0 degrees Celsius, okay, for standard temperature. So I didn't make up the rules. It's just something we use. And the reason why we use standard temperature and pressure, because it gives us a precise number for the molar volume of an ideal gas. Okay, so what is molar volume? Well, as it turns out, molar volume is V divided by N. It's the volume that a gas occupies divided by its number of moles. And as it turns out, at STP, and only at STP, so at 273.15 Kelvin and 1 atmosphere, this value is 22.42 liters over moles. So where does this number come from? Well, we remember we have PV equals nRT. And if I do some algebra here to solve for V over N, okay, I'm going to divide both sides of this equation by N. And also, I'm going to divide both sides of the equation by P. Okay, and so the P's cancel and the N's cancel. And what this gives me is V over N equals RT over P. So what happens when we use our standard conditions? Well, we note R is 0.08206, and look, this is liters times atmospheres divided by mole Kelvin. I want you to get used to putting units in your equations. I know it can be kind of a pain in the butt to do that, but it helps you see that the units cancel. My standard temperature is 273.15 Kelvin, and my standard pressure is 1 atm. So now look what happens to my units. Kelvin and Kelvin cancel, and atmosphere cancel, and what I'm left with is a liter divided by a mole. So now if I calculate that, 0.08206 times 273.15, and of course divided by 1, 22.41 something. So I said 22.42. I'm kind of cheating. I'm fudging the sig figs a little bit. So we'll say 22.415. I'll add in one more sig fig to be super precise, okay? So what does that number mean? Well, that number I can use as a conversion factor, right? What that tells me is if I have 1 mole of gas and I'm at standard temperature and pressure, I know that 1 mole of gas is going to occupy 22.415 liters, all right? What if I have 2 moles of gas at STP? So let's actually write that down. Let's say, what if I have 0.567 liters of gas at STP? So I totally just pulled that number out of a hat, okay? Well, I could use the ideal gas law, right, to solve for those number of moles. However, if I know that it's at STP, and I have 0.567 liters of that gas, and I want to know how much of that gas that I have, look, I can do this like dimensional analysis. I can say 0.567 liters times, I know from this number in, excuse me, let me, I need to write it the other way. I need to flip it because let's maybe say I want to know how many moles I have, right? So in 1 mole, there's 22.415 liters. And look, I can use that number just like I would in my normal calculations. So I have this number in my calculator. I'm going to say 1 over x, right? That flipped that number for me, times 0.567. And so then in reality, I would have like, 0.0253 moles. So once again, I kind of just pulled that number. I just kind of randomly said, what if I have 0.567 liters at STP? By saying it's at STP, then I know I can use this number directly. But if it's not at STP, okay, then I would be plugging in that 0.567 into V. I would have to know what the P and the T is as well, and then that would tell me how many moles of gas that I would have, okay? So pay attention to this STP. It can make our problems much easier to calculate knowing that value, okay? So here's a cool calculation we can do with PV equals nRT. So bottles of compressed O2 carried by climbers ascending Mount Everest have an internal volume of 5.9 liters. So right away, I'm just going to start collecting all my stuff. Assume that one such bottle has been filled with O2 to a pressure of So P equals 2025 psi at, oh, look, T equals 25 degrees C. Also assume that O2 behaves as an ideal gas. We're going to talk in the next coming videos what that means. For now, we'll assume all of our gases are ideal. And that ideal gas means I can use PV equals nRT. And so now it says how many moles of O2 are in the bottle, and then what is the mass in grams of O2 in the bottle. Okay. Well, I can solve for N, and I'm going to do some quick algebra here, and I'll say that N equals PV divided by RT, okay? And that'll get me the answer. But remember, my pressure, I have to make ATM. My volume is in liters, so that's all good. And my temperature, I have to make Kelvin. Okay, so let's do that. So if P equals 25 psi, I remember from my chart, let's take a scan back, that 1 atmosphere is 14.7 psi. You don't have to memorize that, but I've got it memorized at this point. Okay, so let's see, scanning through, good. So that says it was 14.7 psi equals 1 ATM. Okay, so 2025 divided by 14.7, and that's 100. And let's see, I'm not going to count the sig figs in my conversion, but I've got 4 sig figs here. So that's 137.8 atmospheres. That's a high pressure oxygen bottle, right? Whenever you have one of those kind of scuba tanks, don't just rip those things open. That's a for real number. They've got about 2,000 pounds per square inch. It's like a missile when you open one of those things. Okay, that's why you need a regulator, one of those pressure regulators, to keep you from making a missile. Okay, so temperature is 25 degrees C, but I got to convert that to Kelvin. And I can just really easily say, right, plus 273, and that's going to give me 298 Kelvin. And I've got my correct V, so now all I got to do is plug and chug, okay? And so my number of moles, N, equals 137.8 ATM times my volume, 5.90 liters. You know, that's about that big, right? This is one of those backpacking tanks you see all those crazy mountain climbers wearing. Divided by R, so I'm going to use 0.08206 liter, atmosphere, mole, Kelvin. I'm going to keep all those units because I just like to see that they all cancel. And then finally T at 298 Kelvin. Now definitely that bottle is no longer 298 Kelvin on the top of Mount Everest. But if it was at 298 Kelvin when it was filled, that's going to determine how much gas was in that bottle, right? Because it got filled up at 298 Kelvin, closed up, and then it got taken up to the mountain, okay? So now I can see that my Kelvin and my Kelvin unit's going to cancel. My atmosphere and atmosphere, liter and liter. And look, the way this works, this becomes 1 over moles. So that is going to give me a mole. So I'll write that down. That unit becomes 1 divided by moles, which gives me a mole. Okay. So now I'm going to keep this number in my calculator, because why not? Okay, that'll be more accurate. Oops, I said plus sign. Plus 0 equals. Okay, so now times 5.90 and then divided by 0.08206 and then divided by 298 equals. And that's quite a bit. We need quite a bit of oxygen up there on Mount Everest. So 33. And the volume is going to give me 3 sig figs, same with the temperature, 3 sig figs. So 33.2 moles of O2 All right, and we know 1 mole of O2 is 32.00 grams. Okay, so I'll leave that number in my calculator and say times 32. And yeah, it's like a kilogram, right? 1,063. That's a kilo of oxygen you're carrying around with you. So 33.2 moles, or with 3 sig figs, I'm going to write that as 1.06. So look, this is 1,063 grams. And you can see right away how I recognize that was a kilo. Technically, it's 1.06 kilos. Okay. You know, and that's like 2.3 pounds or so of gas. So it's quite a bit. That's why it's under such a high pressure. Okay. Great. Moving on. And so this is now this combined law thing. What is this combined law? So when we were talking, let me back up here and talk about some of our other gas laws, right? Like Harmon's law, P1 over T1 equals P2 over T2. This is with constant volume in moles, right? Or Charles' law, V1 over T1 equals V2 over T2. This is with constant pressure. Or now, Boyle's law, P1 V1 equals P2 V2, and this is with constant temperature. But what if none of those things were constant, right? What if I wanted to think about how all of those things can change? Well, now here's my combined law, all right, where I've combined namely Boyle's law and Charles' law. P1 times V1 divided by T1 equals P2 times V2 divided by T2. And here I'm actually going to place 1 with room and 2 with STP. And so what we can actually do with this, so I talked about that STP number, right? Okay, well, we can use this to kind of easily correct for what that should be. Because rarely, so remember what STP means, 1 atmosphere and 273 Kelvin, which is 0 degrees. So that's like a big giant meat locker, like a big giant walk-in refrigerator. We don't do chemistry in a big giant walk-in refrigerator. You would be very cold if you did that. So that's why I replaced the 1s here with room, because we do chemistry like in a room, right? That's typically 25 degrees Celsius or 298 Kelvin, not 0 degrees Celsius, okay? So in this problem, suppose we measure the volume of 1 mole of a gas to be 35.42 milliliters at a typical room condition, which is 295 K and 0.987 atmospheres. What is the volume of this gas in STP conditions? Okay, so this is pretty typical, right? Where we would have measurements at room conditions, but now we want to scale that up to STP conditions. So let's see how that would all manifest, okay? So now let's see here. So I know, so it's asking me what is the volume of this gas in STP conditions? Okay, so we're going to solve for that VSTP. VSTP, okay? And what I realize is I don't think that this could be 1 mole of a gas, right? That would not be correct, because 1 mole of a gas would have to occupy like 22 liters. So I'm going to say, suppose we measure the volume of some amount. Okay, so I wrote that question incorrectly. So we measure the volume of some amount of an ideal gas to be 35.42 mils. Okay, so we're solving for VSTP, and I'm just going to quickly do the algebra here and write that's now TSTP. Oh, I can't write. Okay, so just to tell you really quick what I'm doing, I'm going to multiply both sides by T over P. So I'm going to multiply this by T. I keep writing, I'm writing like S, and I can't say T while I write S for some reason. TSTP divided by PSTP, right? I'm going to multiply both sides of the equation by that factor to isolate the units that I want, okay? So now this gives me VSTP equals T STP times P room times room, V room, okay, divided by P STP times temperature of the room. And now all we got to do is plug in what we know. So we know TSTP is 273.15 Kelvin. Okay, so I'm going to put that in there, 273.15 Kelvin with all the digits to get an accurate answer. So P room, they tell me the pressure of the room is 0.987 atmospheres, not exactly 1. And rarely, very rarely, even at sea level, here in Humboldt County, very rarely is the pressure actually ever 1.00 atmospheres, right? So that's why this is useful to be able to correct to what the actual standard temperature pressure condition is, okay? And then they measure the volume to be 35.42 milliliters, and this is a situation where I can just leave it in 35.42 milliliters because I don't have the ideal gas constant in this equation. So I can leave it in this milliliters, and the answer it's going to give me is in milliliters. Okay, PSTP we know is, right, exactly, I mean, I could write 8 million zeros. It's 1. It's 1 atmosphere. 1.00000, whatever, okay? And then temperature of the room we measure to be 295 Kelvin. Okay? And I'm going to use four sig figs. I probably should have had one more sig fig. I'll just cheat and I'll say 0.9870, and I'll call that 295.0. And I want to make that many sig figs to illustrate how different this volume becomes. Okay? So 273.15. So the sig figs there are because I didn't write the question very well, not because I'm like cheating the sig fig rules. Okay? So 273.15 times 0.987 times 35.42, okay, divide by 1, and then divide by 295 equals, and now I get 32.37 milliliters. So that's why I knew that there's no way that could be 1 mole, because 1 mole should occupy 22.4 liters, not 32.37 milliliters. So this would be much less than 1 mole of a gas. But all the same, as you can see, when we do chemistry, we're not ever doing chemistry at these STP conditions, right? It's impossible. So use of the combined law is a way of either correcting the STP conditions to the room conditions or vice versa, correcting the room conditions to the STP conditions. It goes either way because of this proportionality. Okay, so I'm going to talk very briefly about the next few things. Actually, I think I'm just going to very briefly talk about this and then I'll cut it off. I'll stick to nice short videos. Okay, so I'm not going to really mention much about gases and chemical reactions in these lectures because we're going to be doing that a lot in our calculations. We're going to be doing a lot in the semester as we continue to talk about gases and chemical reactions. So I just wanted to mention a few examples. Stuff we've already talked about, combustion of hydrocarbon, right? And up to now, we've typically given you, like what mass of carbon dioxide do you get out of this equation? We don't really ever measure the mass of gases, in all honesty, okay? We measure the volume or the pressure of a gas. So a better way to do these combustion reactions would be use PV equals nRT, right? Because we typically will know a volume of a gas or pressure of a gas, not the mass. Airbags. This is actually kind of just one random cool example. So this thing is called sodium azide. Azide is a particularly weird polyatomic ion. It's N3-, the azide polyatomic ion. So obviously I did not make you memorize every single polyatomic ion that there is. There's a lot of them. So sodium azide is particularly explosive, and a very small detonator cap will create a spark with this thing, which causes this sodium azide material to explode. It makes sodium solid, which doesn't really change the volume much, but look, it makes nitrogen gas. And I just said it explodes, but it's not like a combustion explosion. It just evolves gas, and it does it very quickly, right? Because what happens as the car is impacted, this little electronic senses that impact, okay, and releases the detonator cap, which detonates the sodium azide, and very explosively and quickly fills this airbag with nitrogen. In fact, that's why it can break your bones, because there's so much pressure of nitrogen that gets created, and it's so explosive that when you come into contact with that in the wrong way, like your elbow hits the airbag or whatever, it can break your bones. Of course, better than flying through the windshield, right? So this is really cool. Oxygen generators on the space station or even in airplanes and really high altitude airplanes. So we recognize this is sodium perchlorate, okay, which also can undergo a pretty explosive reaction under the right conditions. Okay, chlorates, perchlorate, so ClO3, this is pretty explosive stuff. And mixed with an iron catalyst, it makes these two solids, sodium chloride solid and iron oxide solid, but it generates oxygen gas. So these things are done in a much more controlled environment, not like the airbag that just needs to inflate all that gas at once. So these typically will make oxygen in a much slower, more controlled, non-explosive way. Because of course, if you were on an airplane, the last thing you'd want to do is blow it up by accident because you're trying to make oxygen for people to breathe, okay? So this says, we will explore gases and chemical reactions more in the discussion. So in your discussion worksheets, I'm going to give you more examples. But basically what it comes down to is we use the ideal gas law, right? We solve for N. N is PV over RT. And if we're given some conditions in our chemical reaction, like what's the pressure, what's the volume, what's the temperature, that's going to be able to give us number of moles. And then from there, we can use these balanced chemical reactions in the same way we've been doing. So there's really not a whole lot of difference here, okay? We're just kind of slightly changing the way that we do our stoichiometry by using the ideal gas law to calculate number of moles, okay? So I think I'm going to end the video from there. Let's see if I have my, where did my learning goals go? I'll bring up the learning goals of the next slide and summarize. Okay, folks? So I'm going to anticipate 2 more videos. So we'll have 4 videos in total for gas laws. So I'll anticipate 2 more of about the same length as these previous 2. Okay, folks. I'll see you in the next video.